Good afternoon. Welcome to the Mission Assurance track. It's time for us to start now, so we'll go ahead and get started. We've got 3 paper presentations coming up today that talk about mission assurance related to, most of them are related to cyber physical systems. Thank you. So we're going to start off with our first paper from Captain Willis. He's here from the Air Force Institute of Technology. He's a graduate student there working on his master's degree, and he's going to be talking to us today about a very interesting topic, and we'll see how it goes. Thank you.
Okay, looks good. All right, good afternoon, ladies and gentlemen. I am Captain John Willis from the Air Force Institute of Technology, and I'm here today to discuss a methodology my cohorts and I used in investigating the current trend in satellite security, its limitations, and how additional considerations can be put in place to help build more resilient satellite architectures. I'll begin by first giving an overview of satellite systems and talk about where the current trend in protecting these systems lie. I'll discuss how this trend has led to the oversight of the satellite vehicle and how it may not be as secure as we previously have thought. I'll also discuss how the capabilities the satellite vehicle provides make it a high-value target to our adversaries. And then with this framework in place, I'll talk about the methodology we used to pinpoint cyber vulnerabilities and the generalized architecture we used to then create cyber vulnerability scenarios. In a classic satellite system, it can be broken down into 3 active segments. The first segment, the space segment, includes the space vehicle. The next, the ground segment, includes ground facilities, the control center, the infrastructure, and the facilities. And the last segment, the user segment, includes people, organizations, agencies, and anyone that utilizes the features and capabilities given by these space-based assets. When it comes to protecting these systems, the focus has traditionally lied along 2 paths. The first path involves restricting access and communication to and from the space vehicle, and this is accomplished either through encryption or authentication. And the second path lies in limiting access to the other 2 segments, the user and ground segments, and this is done through physical means such as gates or guards, or done through logical means such as firewalls or IDSs. And both these methods are absolutely essential to the overall security of these systems, and both have been researched pretty extensively by the satellite community, but even together they don't provide a fully comprehensive solution. And looking at the chart, you can kind of see where the gap lies. There's really nothing in place to help protect the space vehicle. And when you look into the research, very little has been done to look at how you could attack and how you could protect the space vehicle. And there's many reasons that the space vehicle is neglected in conventional satellite security analysis. Out of the 3 segments, it undoubtedly is going to seem like the most secure. You have the space vehicle orbiting thousands of miles an hour, tens of thousands of miles above the Earth's surface. Then the moment you add encryption to both ends, it really does start to look like the ideal air-gapped network. And without a doubt, any attempts to compromise this segment are going to be a lot more technologically difficult than its stationary wired counterparts. And one aspect to all of this is that when the space segment is designed, the focus traditionally isn't on security. These space vehicles operate in the harshness of space and provide critically high demand mission capabilities. So the focus has always been on availability. And the moment that you try to add any security into these systems, you're making them far more complex and you're lowering the availability overall. And unfortunately, with satellites being in space, once you can't design any security in after the fact. And so part of the problem, or the big problem with all this, is the assumptions that we've made to neglect the satellite vehicle or assume that it's secure enough are now being used against the satellite community. Previously thought to be impenetrable air-gap networks have been shown to be vulnerable, probably with the most famous of these being Stuxnet. But the recent boon of vulnerabilities against the CAN bus is even more telling. Where these CAN vulnerabilities have flipped the automotive industry on its head, the secretiveness and the classification in the satellite community really do help conceal the fact that similar technologies and often older versions of these same technologies are at the base of our satellite networks. And part of all of this is that in the beginning, satellites were really only a government and state venture. But the decrease in space cost or space launch and the proliferation of technology have really made them far more feasible to academic institutions, the commercial sector, and scientific communities. And this is only compounded when you start to consider in dual-use satellites and standardized bus architectures. So nowadays, when the military is looking for some sort of space capability, they'll often just go and either buy a standardized bus off the shelf, or they'll look to purchase space on a satellite that's going to be largely used for commercial purposes. And this is all to say that the level of obscurity that once could be relied on to help protect these systems is going away. Our adversaries are, much like with what happened with the CAN bus, the systems and how they work and operate are no longer hidden from our adversaries. They are learning, they're researching these, dissecting them, and learning how to harness these vulnerabilities. And then to the final point on the focus of availability over security, many of the mechanisms that we're putting in place to help streamline operations also makes it easier for these vehicles to be attacked and also make it less likely that any attack would be detected. And the focus that we're placing on these really do emphasize the national and economic, how vital they are to our national and economic interest and how much the military and civilian sector rely on them for mission success. The chart here shows the methodology that we started with when looking at cyber vulnerabilities against the space vehicle. For a cyber attack to be successful, there needs to be several conditions in place. The first condition is there must be some underlying susceptibility in your system. Second, the threat actor must have access to this susceptibility either logically or physically. And third, the threat actor must have the capability to exploit this system. All three conditions must be present. And if you have any ability to reduce or eliminate one of these conditions, the vulnerability space will follow as well. So unfortunately, there's not a lot that can be done to reduce the threat actor's capability. These satellites are what they are, and the information is largely out there already. So when you're trying to build more resilient satellite systems, your real focus is going to be on lowering the system's susceptibility or the threat actor's access to these susceptibilities. Our research really began with the assumption that the threat actor had access to the system and focused on that intersection between susceptibility and capability. To help create our vulnerability scenarios, we used the following general satellite architecture. And the real usefulness of viewing satellites in this hierarchical fashion is that the interconnectedness of the system quickly becomes evident, which helps engineers pinpoint security flaws and see susceptibility points. Each of these subsystems works in conjunction with each of the other ones, and so through a series of inputs and outputs. So even if one subsystem is secure, once as you put it into this system of systems, it may no longer be. And our architecture here is unique in the fact that we included the data bus for that reason, which is not often included in most subsystem views. And this can be a grave oversight when looking at overall security. Each of the subsystems in green are the ones that we specifically looked at and are essential to the operation of most satellites. The red ones are essential too, but we didn't specifically look at those. We left the mechanical structure out because it's not often logically connected to the other subsystems. And we didn't look at the payload because depending on the mission capabilities, the susceptibility range can be so varied that it's difficult to make any generalized assumptions. So now with the methodology in place and the generalized architecture discussed, I'll go into each of the vulnerabilities we discovered with a specific focus on those that propagate from one subsystem to another. So the first subsystem we looked at was the power supply, which is responsible for generating and propagating power to the rest of the other subsystems. The power supply is also responsible for telling the batteries how much, when to, and how fast to charge. In the power supply subsystem, the greatest susceptibility is going to be your batteries. Anything that can be done to affect the temperature, the rate of charge, or the level to which these batteries can discharge is going to have an effect on these batteries' life and the life of the satellite. So looking at a possible attack vector to make use of these susceptibilities would be a compromise of the attitude control system and the ability to spoof data. In many satellites, the ACS is connected to the charge regulator, and if you have the ability to spoof data, you can interrupt the charge cycle, thereby causing these batteries to discharge beyond a point that is safe. The next subsystem we looked at was the propulsion subsystem, which is responsible for providing the necessary thrust throughout a satellite's life. For geosatellites and other orbit-specific vehicles, their usefulness is highly dependent on their ability to maintain a specific trajectory, which would become impossible without fuel. So really, when you're looking at the propulsion system, the susceptibility space results from either finding a way to waste fuel or pushing the satellite outside its assigned course, outside trajectory. And this can be done either using the ACS by sending out false signaling, or it can be done by injecting false signals to the satellite sensors. So just as one example, if we use the ACS to send false signals that periodically tell the thrusters to make minor unnecessary corrections, this would be an attack that probably wouldn't be detected, could help deplete the fuel, and prematurely end the satellite's life. The final subsystem that we looked at was the CNDH, which is the main brains of the satellite vehicle. The CNDH is responsible for telemetry tracking and control, payload processing, and system bus management. For satellites that operate with a master-slave type control bus, like the MIL standard 1553, the CNDH is also going to be your bus controller that tells all the other subsystems when they can communicate and transfer data. Compromise of this type of system could propagate to any of the other subsystems very easily. And just as a single example, if your CNDH controls your antenna, you could have it send out false data, or you could have it cease communication entirely. And any compromise of this CNDH is going to decrease the likelihood that your ground segment would have any idea that the attack happened. All the vulnerabilities discussed so far have been largely conceptual, and they're really based on predicting what is possible through looking at known mechanisms and security issues in similar systems. Our adversaries have shown that they have the capability to target like systems, and the vulnerability space is only likely to increase as satellite technology becomes more accessible. With the increased frequency and intensity of these cyber attacks and our growing reliance on satellite capabilities, it's important that we find a consistent engineering process that can help build resiliency into these systems. And it's also essential that we find a way to look at our current satellite infrastructure and our current satellite inventory and see their vulnerability space and find a way to reduce it. And I think the methodology to be discussed here is one such tool that could be used. Going forward, I could see this process being applied to each of those specific payloads we discussed, and you could even go back and start to look at the subsystems already discussed, find more susceptibilities, apply specific actors' capabilities to these. My end goal would be to follow much the same progression as you see with the CAN bus, where these attacks were first hypothesized, then shown to be operational on a bench test, and then actually implement it inside the vehicle. Doing that helped the automotive industry start filling in and fixing these vulnerabilities, and I think much the same could be done with the satellite community. All right, thanks everybody. That's my end of that. Any questions?
Hi, thank you. So one of the lessons learned, of course, that we use when we talk about IT security or developing systems is that, as you mentioned, it's much easier to build security in from the beginning rather than attempt to bolt it on afterwards, both in terms of time and money. So considering the, by definition, remote location of the satellite, if you do discover a vulnerability, how might you go about resolving it or fixing it?
So that's a great question, and a lot of this is trying to find what organic capabilities already exist on these systems that can be implemented after the fact. Really, the trajectory that my research has taken is I'm looking at MIL Standard 1553, and we're looking at the organic capability on there to measure variations in the waveforms to help detect these things. So when you're looking at after the fact, you've really got to try to find what's unique, how it can be used, and what's already on there. Yes, sir.
You had mentioned that one of your primary concerns is data spoofing, that you can get some kind of bad signal or something to interrupt the primary operating capabilities of the satellite. From a defensive standpoint, do you see that primarily being mitigated based on some of the kind of, like you said, the follow-on, bolt-on security protocols that you could potentially install in the software systems of the satellite itself, or do you see a terrestrial-based element to that solution as well?
I think that, especially when it comes to satellites, depending on the orbit and all of that, your communication window can be so small that trying to implement any of these at the ground level is going to be difficult. So I'm thinking that most of this work has to be done at the space vehicle, and that means overcoming a lot of the size, weight, and power restrictions as well. Yes, sir.
You mentioned one of the ways that the attacker could approach this, they have to meet all the categories for the vulnerability to exist. What methods do you think the attackers would have to be able to access the system?
And this is really the technologically challenging part. And there's a lot of different avenues, and I'm kind of waving my hands on it. But like the big one would probably be supply chain management, getting parts in there. You have all the conventional methods that we use to get into air-gapped networks. You could have a rogue engineer. You could have the software upgrades apply some bug into the system. So I know it's a lot of like hand waving, but this is exactly what happened with the automotive industry and the CAN bus, where the researchers showed, hey, your CAN bus can be attacked, and everyone was like, well, there's no possible way that they could actually get on the CAN bus, and then 2 or 3 years later, it blew up in everyone's face. Yes, sir.
With the utilization more and more from GSA and DISA through commercial SATCOM, satellite communications, is there any type of program or dialogue that we're doing right now to ensure DoD some sort of insulation or compartmentalization as far as protection from some bad actors, sending commands or something?
That question may be way above my pay grade, sir. I'm not. Oh, no problem.
My question is, considering all the issues that you're having with this, is the thought process most likely in the future going to more microsatellites that cost significantly less or easier to get up and down so that you can change hardware and update software to avoid issues?
Absolutely. Microsatellites and not relying on these multi-million-dollar systems that you expect to be up there for a decade at a time is really the way to go, because many of these geosatellites, you look at GPS or you look at our infrared sensors, they've been up in space for 10 to 20 years, And it's hard to imagine trying to protect something for that long. All right, any other questions? All right, thank you very much.
All right, thank you, John. Very nice. So there are some similarities between the industrial control systems we have down in our power plants, our water treatment plants, and the satellites, and that they are used for a long time. Our next speaker, Antoine Lemay, is going to talk to us about a timing-based covert channel for SCADA networks. Again, using objects that are in the industrial control system network, maybe to some nefarious type needs. Antoine comes to us from the Department of Computer and Software Engineering at École Polytechnique de Montréal, and he's here to talk to us today.
Thank you very much. I'll do my best not to cough into the mic. Sorry. So, as was said, my name is Antoine Lemay. I'm from École Polytechnique, which is the building you see there, but the work was done in collaboration with Professor Scott Knight from the Royal Military College of Canada, which you see in the small corner on the left. So what I'm talking to you today about is a timing-based covered channel for SCADA networks. The previous presenter said that at some point during the process, somebody theorizes a vulnerability, then they go to bargaining and denial, and then eventually someone builds it. So basically, what we're trying to present here is something that we have built to demonstrate these particular channels. So the outline of the presentation is as follows. We'll start with a brief introduction to SCADA systems, because I'm not sure if everyone here is familiar with them. And then we'll talk a bit in more detail about the operational scenario. And then we'll describe why specifically a time-based covered channel in comparison to other channels. And then we'll talk a bit about our implementation and the results. And we're going to talk if this could happen in real life. So in terms of introduction, this is what you would call a typical SCADA network. This is inspired from what you could see in the power grid. Basically, you have a bunch of enclaves, each of the different substations, where you have the level 0, which is the actuators and the sensors that are literally physically plugged in the system, which are these are the programmable logic controllers. So these actually do some local control. All of them are aggregated in a remote terminal unit. And then you're crossing some kind of boundary so that you can traverse on the wide area network to go back to the control center, where there's a master terminal unit that will regularly query all of these substations to gather a state estimation of the system. So basically, you have this local control that is physical here, and then you collect all of them for a supervisory capacity somewhere in the control center. So in terms of the power grid, for the power grid, this is where the mission happens. This is their production system. And ultimately, if I'm an attacker, this is where I want to be if I want to create physical impacts. So there's other kinds of similar networks, since we're at a defense conference. This is basically the same, where you have a vehicular network or a CAN bus, like the previous presenter said, and you've got a bunch of these small networks. Each of them has an antenna that creates a boundary, and you're communicating via Wi-Fi, and you go back to a central command center. So basically, the architecture is the same, and the concept which we'll abuse is the same, meaning that for all of this to be relevant, you need to have some regular communications going from the centralized situational awareness to the vehicular network that's asking, what's your status? What's your status? What's your status? And you've got regular status updates. So why do we want to build this? What's the operational scenario in which that particular channel would be relevant? So if you're talking about real operation, as I said, where you want to have your impact is directly on the plant land. So this is where the physical impact is. For example, I've snuck in through I snuck in a compromised board through your supply chain, and you've installed it in all your vehicles, and then I want to be able to stop your vehicles if they're ever facing me. So I've got an implant that's on the physical part of the system. However, if I want that implant to do any work for me, I need to be able to communicate with it. I need to be able to update its tasking. I need to be able to say, this is now the moment you need to activate. And I need to be able to say, well, there's a new system going on. They've upgraded these other boards, so I need to upgrade my implant to reflect the new state of the network. So I need to maintain command and control. I need to maintain communication with that particular system. But these systems are not directly connected to the internet. These systems are protected enclaves that are behind a firewall or some kind of barrier or some kind of air gap. So I need to go through a pivot point that is a place that that is connected to the internet, and typically this is the command center LAN. Because you don't want your SOC operators not to be able to send their email at the same time as they're looking at their screen. So usually you'll have these systems that have some kind of bridge between the corporate network or the internet and the production network where they do most of their work. So we've got a compromise on the control center, which acts as a bridge on the internet, and we've got a compromise on the physical system or the plant LAN where we have an implant, and we need to maintain command and control. So what we're interested in is this particular communication between the implant and the pivot. And this is why we're going to build, this is why we need to build a covered channel that runs on industrial control systems protocol. Because as I said, there's a boundary there, and the only traffic that goes through here is industrial control system protocol traffic. Also, because we're crossing a boundary, there's the possibility that somebody might be looking and trying to detect us and kick us off the network. So there's a warden that's looking there. If you look at historic example of this kind of scenario, for example, if you look at Stuxnet, Stuxnet was heavily invested in stealth. There were multiple rootkits on there. There's a custom PLC rootkit that was never before that required lots of effort to be able to hide the fact that the system was compromised. But this particular traffic, there's really lots of traffic for Stuxnet. There's not a lot of stealth on the network domain. Why? Because nobody's looking. But as the systems progress, people will be looking more and more, and we need to be really covered. So that's why we're building covered channels on this particular bit. But why use specifically a timing-based covered channel? So the operational scenario that we have is a scenario of strategic prepositioning. I want to preposition the malware until I need to activate it in case war happens. Now, war might not happen today, might not happen tomorrow, might not happen within 50 years, but who knows? Maybe somebody got hold of Twitter and suddenly we're at war. So we need to be prepared for any eventuality. So we need to stay undetected for a very long time. The dwell time inside these systems is very large, and you need to be able to make sure that you're not kicked off before you can do the damage that you expect to do. So the timing-based covered channel evades typical network artifacts that can be easily observed. In particular, we're not opening new ports, new random TCP ports. We're not injecting new packets on the system, and we're not altering the packet entropy by jamming a bunch of information in otherwise low information packet. So these are the easiest way to be able to detect. So we want to be able to avoid this. And normally in traditional IT networks, we try to avoid timing-based covered channel because they're very hard to implement, because there's lots of people do very random stuff on the internet, so it's very difficult to be able to accurately measure what delays are and what the jitter is. However, in industrial control systems, it's much easier to implement timing-based covered channel. Why? Because the regular situation update that we were talking about, the regular polling that is done by the system to implement these systems creates a reliable time reference against which we can measure delay and against which we can reliably use the delay to transmit information. So what we built is an interference-based implementation. And what do we mean by that? We mean that we have the regular control system, which is the master terminal unit talking to a PLC or RTU. And basically what we do is we take that normal communication and we interfere a bit with that communication to add a slight bit of delay, and we interpret that delay. So this is completely transparent to the control system. There's multiple ways we could have this, but because it was the simplest to implement, we did a network man-in-the-middle based approach, where basically we intercept, for example, the MTU is sending a polling packet. What's your status? We intercept that packet. We add a delay based on the information that we need to carry. On the plant LAN, it's also intercepted on the other side. The delay is measured, and the packet is transmitted to the system. To this system, it's exactly the same as if the packet was received during normal communication. So it's sending an acknowledgement packet to get on the other side. This acknowledgement packet is intercepted by the implant. There's a delay added based on the information. It's intercepted by the pivot point, and so on. So this would represent some of the normal ways in which you would compromise a system, meaning that it's very unlikely that you can have full system compromise and you have complete access. You can replace all the software. You have access to all of the software. You can just Trojan everything, and you completely own the network. So normally you have partial access, and we wanted to reuse as much as possible what was already there, so that we did not need to change the software on the MTU or change the software on the PLC, which might be ladder logic or something weird. So, but ultimately, this concept would be exactly the same if instead of having a network man in the middle, I had compromised this machine and I can hijack the network card, or if I can just hijack the software. So this is the same system. The reason we built the network is because it was easier to implement. So what does it do? So to test this particular implementation, we executed Linux command back and received the results. And basically what we did was we executed the ls command. So we're sending 3 bytes from the MTU to the PLC. And based on the result of that particular ls command, we're sending back 16 bytes. So we're sending a very small amount of information. And to complete that entire transaction, you can see that it's around 3.5 minutes to complete that particular transaction. So we're talking about very low bandwidth. We're talking about something like 0.2 bits per second in terms of transfer. And you see there's like huge dips there. These are places where the channel actually crashed because there's no error correction. And this is where some errors occur that could crash the channel. But for the most part, you see around 30 runs, most of them were completed, and it were completed successfully. So the channel actually works. But what do these results mean? So first, the fact that it works and that the SCADA system is completely unaffected means that it's really possible to actually use this as a form of command and control channel. We can actually send command and get back results. And also, it's because it's transparent to the regular user, so it's not very evident to detect. As I said, however, the throughput is low. That means there's certain types of offensive operations that this kind of channel is not suitable for. In particular, no software updates, no data exfiltration, no uploading, running VNC on a tunnel with full graphical access. That is out. However, if I just want to update my tasking, if I want to say, well, I need to upgrade my system, so just for that particular time, I'm going to open a high bandwidth channel that is easier to detect, but I'm just going to open it for that particular topic, or to do command line session if you're not in a particular hurry. These are all possibles over this kind of channel. And currently, the error rate that was calculated was 7%, but the implementation that we have did not implement any error detection or error correction. So you could reduce that error rate significantly, almost to zero, by implementing more coding, but this requires more signaling, so this would slightly lower bandwidth. But not necessarily by multiple orders of magnitudes. Maybe you cut the bandwidth in half or something like that. And the other thing is we did a Python implementation that we tested over multiple virtual machines running on the same laptop. And ultimately, this introduces a lot of delays and a lot of measurement error. So if we were to be able to implement that full C implementation would be much more reliable in terms of timing and would introduce much less error. So basically what we can see is that this type of channel is a channel that is tilted towards stealth rather than performance. So it's best used in a hybrid scenario where you use that kind of channel for very long dwell time and activate much higher bandwidth channel for specific periods of time whenever you need the performance. So all of this was done in a lab, but could this happen in real life? Could it happen here? So in order for us to test that hypothesis, we had an industrial partner, which is an energy distribution company in Eastern Canada. To give you an idea of the scale, there's about 2.6 million polling exchanges in a 6-hour period. We're talking about gigabytes of SCADA traffic per hour. And basically, if you look at this curve, you see that this is 1 millisecond represents almost half of the traffic in terms of delay. And you see almost all of it is under 100 milliseconds. So, oops. So in these particular systems, because of the operational constraint, these protocols are time sensitive. When people are implementing them, they make sure that there's absolutely no delay, no jitter, no nothing. So the actual reference in the production system is more reliable than the reference we had in our lab environment. So this would mean that this could definitely work in a real system. So this is what I have, if you have any questions.
Hello.
Sorry.
So that same reliability, though, in the last chart also makes you potentially easy to detect, right? If you start adding delays that are over 100 milliseconds, that's an anomaly that could easily be flagged. Is that correct?
That is correct. Again, for all of these covered channels, they're very easy to detect once you know what you're looking for. So depending on the features that you're looking at, it's different. However, there's lots of technology that is currently available to detect new network packets. There's very little that is measuring delay.
Would this attack also work on SCADA systems that are connected via satellite? Would that actual delay of going up to a satellite and back down, would that disrupt it? I'm asking this, I'm a little bit, don't quite fully understand the steps that the delay, where the delay is added in these steps.
So it works in any system where the delay is constant. So in satellite systems, the delay is very long, but if you don't have any jitter, it can work. So basically what you do is when the packet is sent, you intercept it, you hold it for a while, and then you retransmit it. And basically you're measuring, you're estimating on the other end how much time you're holding the packet. So as long as, so if I add 200 milliseconds because I'm on a, or 300 milliseconds because I'm on a satellite, if it's always 300 milliseconds, if I measure that the delay is 700 milliseconds there, I subtract the static 300 milliseconds, and I can see how much time I've held the packet. However, if it ranges between 50 and 500, then it becomes much more difficult to measure how much time I've held the packet, and you get into probabilistic coding, and so you just further reduce the bandwidth. But it could theoretically function on satellite systems.
I'm just curious on your thoughts as to the scalability of this tactic. So if you look at take an electricity utility as an example in terms of the number of RTUs that are out there in the system and that kind of stuff, is the presence where it's located next to the switch allow for scalability, or is it something that you could corrupt the communication between a handful of endpoints, but it would be more difficult at scale?
This question is a bit more difficult because it's not a question of channels, it's a question of what you're actually attempting to create in terms of impact.
Sure.
If I want to take down the grid, how many substations do I need to compromise, which is a different question altogether, and that depends a lot on how the grid is implemented.
Sure.
So technically, this is a method purely for doing this single part.
Okay.
So maintaining command and control over implants behind essentially air gaps. Mm-hmm. So if you look at historical example with the grid, they haven't really needed to do that a lot because they just extract the VPN credentials, and whenever they need to go in, they just connect via VPNs. But but Stuxnet was required to do something like this. So it really depends on the particular scenario.
And I think
I'm sorry if I don't really
No, not at all. I mean, I think that's the relevance of the question, is that to create a short-term grid outage just by generating a voltage collapse by targeting one or even a handful of substations, you could create at least a short-term voltage collapse. And I guess that was the root of my question, is trying to get a general sense that if you were trying to affect a significant number of substations simultaneously to create, it'd be even more difficult to track and potentially have a more significant consequence. That's what I'm curious about just how far you could potentially scale if you were able to effectively implement based on grid architecture.
Yeah, well, again, it depends. So I can give an example from the power grid in Quebec. So some guy at some point was doing a training on emergency measures and fat-fingered, instead of using the training system, he used the production system, and he just kicked off 200,000 people off the grid because by accident.
Right.
So because he used the production system. So there's amazing stuff you can do.
So given that we can't really update the firmware on the PLCs, there's some other things in the system that we can't necessarily update, how could we defend against an attack like this from the systems that we can update?
Much like traditional covered channels and normal computer architectures, you can never completely eliminate the channels. The thing you can do is you can manage their bandwidth and you can monitor them to make sure that they're not used to do anything bizarre. So in any case of high mission assurance scenario, the really best thing is actually not to patch any of this, because anyway you can't, but is really to be able to be aware that this problem can exist and to make sure that you monitor for that particular problem and be able to do something if that particular problem is detected. And there's multiple solutions that are not necessarily cyber. So let's say you're at war with Liechtenstein and you see that these Liechtenstein hackers are in my system trying to do this. You can do a kinetic response on Liechtenstein and achieve similar results. So thank you very much.
All right, so we've talked about critical infrastructure in space. We've talked about critical infrastructure on land, and now we're getting ready to talk about critical infrastructure at our seaports. So our next group of speakers that are going to talk to us today are Mr. Dan Trimble. He's the president of BitLens Incorporated, which is a research and advisory firm specializing in assessing strategic cyber risk and policy. He's got a background of over 25 years in the military and the intelligence community and cybersecurity, high tech, and public policy. Joining Dan will be Jonathan Munkin. He's the Senior Director of System Resiliency for PJM Interconnection, one of the largest wholesale electric markets, and former Director of the Illinois Emergency Management Agency. And also Mr. Alexander Sand, a regulatory lawyer with Evershed Sutherland, specializing in cyber financial crimes, and who was previously a capital markets lawyer with the state of New York. So they'll be talking to us again about the C version of critical infrastructure.
Apologies for hobbling. Never fly cross country after tearing your ACL.
Stand the whole time.
We'll just rotate. Okay. I'm going to stand and talk. That's okay. Thank you, everybody, for coming today. Again, my name is Dan Trimble. The three of us came together in January of last year as fellows with the Madison Policy Forum in New York City as cybersecurity research fellows, where the objective of our research was to identify cyber risks in critical infrastructure and key resources, and to develop a model for how to assess, contain, and mitigate that risk. We chose maritime critical infrastructure in particular, and by that I mean shoreside critical infrastructure. We didn't look shipside at all. But we chose that because there are few, if any, sectors of critical infrastructure that are, shall we say, more economically consequential. If you look at the United States alone, 95% of all economic trade flows through our ports, where extremely complex and highly automated networks take over container movement from the ship through the port and into a much broader intermodal transit system that includes trains, trucks, and a whole variety of interconnected and codependent systems. The controlling infrastructure is heavily ICS. It is industrial control and SCADA systems, but it has really mission-critical operational dependencies on the electric grid, which is where we're going to be talking about in just a little bit, and also on other outside networks that we'll also discuss. One of the other key points that's important to draw a distinction between, there's a difference between ports and port operators. As we're looking at these policy models for how to actually assess the risk in this domain, we had to differentiate between the two, because you have the port operators that run the actual facilities, container movements, the actual operations inside the port. They're heavily regulated. There are any number of different security laws on an international and domestic scale that allow the enforcement of minimum security measures. It's mostly physical security. It's not cybersecurity. So we looked at ways using existing authorities that are already codified under those existing laws and regulations to be able to extend this into the cyber domain. And on the flip side of that is that if you have those that is at the port operator level, at the port level, the port is typically a government or quasi-government entity that leases land for a living. That's all they do. And the truth is, more often than not, they have literally zero awareness of what's going on in terms of critical infrastructure or technical networks and operations within the actual port operators themselves. There's a significant gap there in terms of policy coverage and how you would actually mitigate cyber risks that might start in one of those networks and then cross over into the other threshold. The threat is not insignificant, it's not theoretical. There's two things, one very timely that are worth mentioning as examples of how this has manifested. Just a few months ago, at the start of the summer, Danish shipping giant APM Maersk was hit with a NotPetya ransomware attack. They suffered a $300 million financial loss. 17 of their shipping container terminals around the world were shut down partially or entirely, unable to accept any orders. And every network for every single business unit of this massive global company was impacted in that attack. And that has direct repercussions across huge sectors of not only the U.S. economy, but others as well. And then another example, back in 2013, drug cartels actually hired hackers to maintain persistent access into the SCADA systems controlling the port of Antwerp. And they use it to modify the manifest lists and control which trucks of their own choosing certain containers ended up moving onto from the ship into the port and then onto the truck. And they did this for, I think it was better part of 3 years, funneling almost $400 million of drugs, money, and weapons completely undetected. Those are just kind of two timely examples, but the threats could also be a lot more draconian than that. It's certainly possible for a cyber attack targeting these kinds of networks to release dangerous chemicals, which are quite routinely transported on the sea, or even to take control of ship movement. Our research uncovers significant regulatory gaps, but also a lot of opportunities as well. Areas where existing and already codified laws and regulations can be extended to encompass physical security as well as cybersecurity. And we're going to spend the rest of our session talking heavily about that. And the ultimate outcome is that we're proposing the formation of a maritime cyber assessment organization modeled after classification societies, which are a centuries-old form of public-private partnership in the maritime industry that's worked extraordinarily well to maintain and improve safety of life at sea. And we'll talk a little bit more about that. But the whole purpose of this public-private model is to shift risk assessment to a joint public sector, private sector authority entity to incentivize industry and also to be able to overcome some of government's inability to hire cyber talent at market rates. And I'm going to turn it over at this point to Jonathan, who will talk a little bit more about the threats and the vectors. Thank you.
Thanks. So as Dan mentioned, this is something that we recognize just from a general sense of importance as to why ports are targets. The more important something is, the more likely it is to be targeted. And certainly we see some existing vulnerabilities and then some growing vulnerabilities as well. One of those growing vulnerabilities is the increased interdependency of port systems and some of the surrounding critical infrastructure systems. Specifically, electricity is an example that we'll expand on a little bit right now. So as you look at the trend line right now for the energy usage for ports, it's increasing dramatically. So what they've seen is a near twofold increase just in the last 5 to 6 years on average for US-based ports. What they're anticipating is another twofold increase in the following 5 to 6 years. There are several drivers for that. One of them is related to the increased automation that's being utilized at all the ports. So whether you're talking about the crane operation systems, the intermodal systems that are there, and then just the general level of automations of connected devices that are being employed to overall increase the efficiency of the port operations at each of these locations. Another reason is new regulations specific to the use of shore power, or cold ironing is what it's referred to, which is when ships come into port, typically what they do is they shut down their primary generation source, their primary engine, and then function on diesel backup generators for any of the electrical systems that they need to utilize in order to offload or onload cargo. However, those diesel generators produce a lot of fumes. They produce a lot of carbon. And so there are new requirements now that they have to hook up to shore power and use that electricity instead of running diesel generators or backup generators on the ships. Well, the result of that has become those huge spikes in electricity demand at each of the ports as ships are requiring this land-based connection to power in order to function while they're in ports and doing those intermodal operations. So what this has resulted in is there is now a significant build-out of electricity infrastructure in close proximity to each of these ports to properly service that demand. So if you look at examples like the Port of Long Beach and the Port of Los Angeles, they are going through a massive overhaul of their electricity systems that are in close proximity to each of those ports to make sure that they can deliver on the electricity requirements, the growing electricity requirements on each of these ports. In terms of what this electricity is being used for, in addition to those port operations related to things like shore power and cold ironing, you also have significant demand for things like refrigeration, lighting, and then ultimately the container movement operations. The container movement operations are the single most costly operation if you choose to interrupt those, and they are also the most directly SCADA-based in terms of how they function and what they do. The important thing to highlight here is that in order to badly affect the port, you don't have to touch the port itself. All you have to do is touch the grid, as an example. And if you can affect power flows to that particular area, you can still have a similar effect. So when you look at the size of the attack surface area for ports in general, based on the business structure that Dan just mentioned, which is there are port operators and then there are people who actually own the components that are located on those ports, whether it's the crane systems themselves or any of the shore operation systems. Because of that difference in ownership, there's also a lack of oversight in terms of who has responsibility for what for protecting those systems. And as these interdependencies continue to grow, you run into this and exacerbate that problem even further, which is there is right now there is no joint operational practice around cybersecurity related to all of these physically interlinked and in some cases IT interlinked systems around these ports. What's happening also now is as this additional infrastructure is being built to support this increase in electricity demand, with this new construction of physical infrastructure, there's also the probability of increased linkages between IT systems. So Antoine did a great job of terrifying me with his presentation because there was going to be new substation construction either on site or just outside of each of these ports, which means you're going to need new RTUs and new units that are located just outside of these port facilities. So the question is what level of responsibility for crosstalk is going to happen, and then how is that electricity going to be metered on the property itself, recognizing that whenever you have large individual points of electricity demand, it requires the resulting metering happening at each one of those locations. So any opportunities there just increases the overall attack surface area associated with the ports in general. So plenty of new opportunities for Antoine to go and break some new systems for us. So I'll give you a call when we get some of those set up. So that in and of itself is certainly problematic in terms of how it manifests, but I can tell you that in terms of how it's going to be addressed, this is what we want to look into of trying to figure out when you have disparate areas of ownership in terms of who has responsibility for these things, different responsibilities for operation of the equipment itself, and how these are going to be linked together. It's something that needs to coalesce around a really single set of standards as much as possible to understand that if you're going to be connected into this larger universe of IT-connected devices, you need to have some type of commonality of thought related to not only how you protect those systems, how you identify the potential risks to those systems, ports and points of entry. When I say ports, I'm not really talking about seaports at that point. We're really just talking about some potential linkages to the system as additional things like Internet of Things devices are connected there. And then ultimately, how you would implement a cyber response in that type of environment. So just as you have many different overlapping areas of business authority or lines of or chains of ownership for each of those things, you also have within ports very, very strange rules as it applies to jurisdictional authorities, depending on who owns the vessel that's connected, who owns each of the individual systems that are connected to it, trying to make sure that we have a commonality of thought in terms of how we would approach that. So the good news is we have somebody who's going to solve all of those problems for us. His name is Alexander Sand, and he happens to be the next presenter.
I don't know about solving all of those problems, but
most.
these were definitely the problems we're trying to think about. So, sort of the idea of how we came to approach this subject, right, is we know this is a uniquely difficult area from the perspective of how much specialization there is, how much overlapping dependency there is, using electric as a prime example, how much complexity there is in terms of the operators involved with port as well. Dan sort of quickly alluded to it, but you've got sort of the people who own the port, but then you've got all this different array and layers of folks who are actually carrying out the operations of the port, many of which are private, don't necessarily want anything to do with public, or sort of the government piece of things. It's inherently cross-border. There's just a ton of issues. And we think that these are issues that sort of ripple out. And so we wanted to use this as a test case for the kinds of new thinking from a policy perspective that we could do to try and tackle some of these cyber-specific challenges using this as we think, a really good case study. So we were starting from that point and saying, okay, from a policy perspective, what is going to work to try and tackle some of these? So as by way of further background, then you have to start thinking about, okay, well, we're going to need some sort of legal regulatory hook, which is why the token lawyer is up here. But how can that function? And if we're trying to put in place, or at least come up with ideas that can be built on how to put in some sort of new function and framework and regulatory force to try and address these issues, what tools are available to address that? The realities of Congress and lawmaking and government budgets are that if we really want to address this very current risk and very current issues, we need to find ways to work within the existing regulatory frameworks to address that. So quick background on regulation of port and port operations as it exists now. The maritime domain is subject to a varied patchwork of federal, state, and municipal regulation. There are no one body at any level that really owns all of this. There's so many different stakeholders, both public and private. Sort of illustrate that, there are at least 8 federal entities that have some jurisdiction over the maritime domain. The U.S. Coast Guard, as part of DHS, is the one that's tasked with regulating and enforcing that maritime port security portion of it. Now, as we've alluded to, that generally has focused historically on physical security issues, and that regulatory framework was really built around the concept of dealing with physical security issues. Certainly the Coast Guard and DHS broadly have been doing a lot just in the last year in terms of starting to bring cybersecurity into the focus of that conversation. There's some proposals around rules in terms of adding cybersecurity as a component of existing risk assessment or security assessment requirements, and still focusing on the information sharing pieces of it and trying to facilitate that information sharing. But that's a long way off from what we're saying about, okay, how do we find what is an acceptable and set what is an acceptable minimum standard for being to participate in this ecosystem that is responsible for the daily movement of, what is it, Dan, 2/3 of our GDP, something like that? I mean, the fact that most of our economy is flowing through ports, and we've got incredibly varied stakeholders and no common subset of organization or expectations around how security happens for our IT systems, that's a big challenge. So U.S. Coast Guard, in its role as enforcing maritime port security, does have some powers. They have the ability to promulgate and enforce regulations. As part of this authority, the U.S. Coast Guard and captains of the port have the ability to review and evaluate the security practices of foreign ports or of vessels that are coming into port, and based on, you know, if they accept or feel that those live up to their expectations, they have legal options in terms of what they can do about that. And that includes being able to either refuse entry to a vessel or detain a vessel. So there are some of those mechanisms in place. They have focused on physical security, but there's nothing in the authority and the regulatory vehicles that exist that would prevent them from extending that to cybersecurity. So this is that U.S. Coast Guard mechanism is sort of what we have. And then as we think about how do we then go about using this in a useful way that's going to appease and be able to work with this hugely varied set of stakeholders and deal with something that is inherently cross-jurisdictional, what is the approach that's going to work out? And in the maritime domain, joint public-private partnerships really stand out. maritime sector in particular has an incredibly strong tradition of enforcing safety standards through private means. So this is where classification societies come in, which Dan knows a whole lot more about than I do. So please jump in if I'm going horribly astray. But basically, these were international private organizations were saying, just sort of in the interest of everyone having to deal with the inherently unsafe sailing the high seas, we're going to start developing market-driven, industry-understood standards, and we're going to have an independent assessment, classification of whether or not your ship is meeting those standards. We're going to give you a grade, and then that information is out there, and it's up to the market, basically, to say, well, is that good enough for us? Are we willing to take on that risk? And because of the nature of the maritime domain, it's hard to do better than that. Everything is constantly cutting across those legal jurisdictional boundaries. So that was a good place that we wanted to start, but at the same time, you need some hooks to use that enforcement, give sort of a swift kick in the rear for folks that maybe aren't interested in thinking about a whole new topic or dealing with this new cost center to have to figure it out. So the balance that we came up with that we're suggesting is something called a Maritime Cybersecurity Assessment Organization, an MCAO, Joint Public-Private Assessment Standards and Support Entity. So it would be like classification societies in terms of work with both government and industry to develop standards, expectations about what's going to happen, or what best practice should be, and then be able to go out to port infrastructure and rate against those standards. Be able to understand the risk and see the risk that is present at our port facilities, including those cross-sector dependencies. The idea that would then potentially hook into the existing regulatory mechanisms by having the ability, it's similar to some of the things that are done in the financial regulation side, where you can have these organizations that are public-private partnerships be officially sanctioned and authorized by government through their regulatory ability and say, okay, everyone that is subject to regulation in the U.S. ports, you're going to have to be a member of this organization. We're going to expect you from our existing regulatory perspective to be able to meet those standards. But we as government are not going to be entirely saying what those standards are. We're going to let that public-private partnership do a lot of the development behind that. And so then that lets us take advantage of some of the benefits and avoid some of the issues of trying to do it government only and avoid some of the issues of doing it private only. So private organizations can be more competitive in terms of hiring talent. They can leverage industry experience and knowledge. They can potentially stretch beyond U.S. borders. It's not just a U.S. government entity inherently. It could potentially be adopted more widely. It could be a resource and provide support both pre and post breach for its members. So have the ability to have some of that funding and say, you're not just doing this because you have to, you're also going to do this because we're going to share the risk and we're going to pool resources so when something is going wrong, we have a cohesive, experienced cross-sector team that can go out and then support that security. But it still has that weight and government hook behind it of saying, you all have to participate in this. So that is the approach that we came up with to try and deal with some of those issues. And that's going to be talked about in more detail in our paper. And we have 3 minutes. I only went slightly over. So now it's questions, if you have them. We're going to wait for them. There's some questions now.
Do you have a sense of how much of our critical port infrastructure is owned by foreign entities, including foreign entities who may not be our best friends?
According to the New York Times, there was an article, if I remember correctly, back in 2012, somewhere around 60%, give or take.
It's disproportionately owned. There are more foreign owners of port operations in the United States than there are U.S. companies.
And the largest shipping companies in the world are not U.S. companies. Like APM Maersk, I mentioned a few minutes ago, is a large Danish company, for example.
Do we have a sense of how many are more actively semi-hostile to us?
That's harder to say because the numbers are not official numbers, and since ownership, of course, can be divvied up across multiple countries and multiple entities.
It is an area of fairly significant growth for Middle Eastern countries in terms of port operations, generally speaking. And then Chinese companies are also doing something similar as well.
Shipping in general has a grand tradition of very purposefully confusing and opaque ownership structures as well.
Hi, a couple questions for you. First off, I'm a little surprised to hear you talk about maybe lack of standards isn't quite it. In some respects, security of information systems, it's a well-known problem with a whole alphabet soup of standards out there. You got NIST, you got DoD, you got, as far as industrial control systems, you've got NERC out there. How do you think you might be able to use what already exists or apply it to this domain?
Yeah, so I think a lot of that is very important to leverage existing standards. As a cyber regulatory person, including someone who has written some of my own regulations trying to set standards on some of this stuff, I think often it's talked about as when we talk about, oh, there's standards, or, oh, I'm compliant with NIST. I hear compliant with NIST framework all the time, and it drives me nuts. Because we talk about standards often, but they're very high level. They're very over-the-top general practices. A lot of that can definitely be leveraged. Some of the basics about how you do a risk assessment, how you quantify and grade risk, evaluate inherent versus residual risk. A lot of that can definitely be leveraged, but when we're talking about there's no existing standard, we're saying ports are its own very important thing that have their own very important unique characteristics and risks that don't necessarily exist elsewhere. And when we're talking about something that's so important to just the daily functioning of basic society in our country and the economy and GDP, it's worth having the collection of talent and specified standards to say, you are one of 5 companies in a port operating cranes that are taking things off. Here's our expectations for how you operate those systems and how you secure your specific interaction between public-facing systems, SCADA systems, industrial control, the whole. So getting to that level of specificity and being able to have the cross-sector experience-specific talent to be able to go in and give you a meaningful test and support for securing those systems is not something that I would say exists.
The cross-sector is worth mentioning again because NIST, by definition, is a framework. And even in cases where the standards are getting down into specific enough details, it's typically relevant to that network that it's looking into context in. It's not taken into context of all these interconnected systems, these interconnected networks. There are no standards codified for intelligence sharing from the electric providers downstream into the port operators or vice versa. So standards needs to be thought of much more broadly than just this is what that RTU needs to do and how it needs to communicate and how data security is handled and how the container manifest system is handled. It's a much, much bigger integrated picture that has to be evaluated.
Last question for me, at least for now. Something I saw yesterday at I guess the pregame for this conference. The Estonian foreign minister, whomever it was, spoke about the country's reaction to the hack, 10 years ago. One of the two of the characteristics or the techniques, if you will, that they used to kind of help get through that, or a couple of the themes that characterized the Estonian response was transparency, partnership, and collaboration. How do you think that might apply here, especially considering what I think what you mentioned was the sort of broad gap between of sort of knowledge and recognition of the problem between all the shareholders?
I think it's the cornerstone of the problem, honestly. So each of those 3 things, transparency, partnership, and collaboration, is totally essential to any degree of implementation in this particular type of environment. So while there's say a transactional or an economic integration, Southern California Edison is the electricity provider for the Port of Long Beach. In terms of the next stage,
even though they are a NERC-compliant organization or a FERC or NERC regulated, or in that case, California Utility Commission regulated entity, the port that they're interacting with is not. Not that Southern California Edison can only interact with people who are regulated assets, but in terms of individual users on their system, the Port of Long Beach is one of the single largest consumers of electricity in the whole of South California. So the question is, for something of that significance or that comparative importance, what type of collaboration is necessary? And that could be in terms of the implementation of security protocols on their systems. It could be that operational integration or intelligence sharing that happens that right now is not a required part of what they do.
And that's exactly the issue that we are trying to think about how to solve in proposing the creation of a public-private partnership, is trying to find a way that's going to facilitate that cooperation across stakeholders that isn't going to inherently pull apart necessarily. And so being able to get that benefit. If I know we're over time, but I know she's been trying to get in a question from the very beginning. Right. Still have it.
Yeah.
The Coast Guard and DHS and a number of other entities are certainly looking at cybersecurity. They're starting to promulgate a number of different ideas. They're starting to have open hearings on proposed regulations. There's definitely motion happening on the government side. Our research is not saying that that's not happening. Our research is saying that there's a significant private sector and public sector interest in working together to solve a lot of these problems. And it's not to say government's not working the private sector, they are, but there needs to be a more coordinated effort, we believe, to tie some of this responsibility back to the private sector, because you're right, all the regulations won't necessarily compel a foreign entity to participate in that. That's one of the things that has actually worked historically for classification societies. The markets incentivize the participation because the lack of meeting certain standards is an acknowledged problem.
And
Sorry,
please. So I think sort of inherently in what you're saying is why I think we're proposing sort of maybe a more independent model of that public-private partnership. So as you're saying, sort of if it's DHS, then other countries aren't necessarily, other institutions aren't necessarily going to be receptive to that. Same thing for the, we were talking about how most of the port operators and shipping companies are foreign companies. There's going to be tension there if it's seen as a DHS vehicle, even if it's a public-private partnership. So looking to some of the examples that we see in the financial sector and other places where it really is a standalone, self-funded organization that has equal representation in terms of governance from both public and private, that shifts some of that tension, and it becomes not a partnership that is a DHS function, but something that is leveraging the authority that exists through the Coast Guard to encourage participation, but really is standing on its own. And
it's
so
really about leveraging the strengths and weaknesses of each sector.
Sure.
No one's going to solve this by themselves.
There's models of practice around that in the utility industry as an example, which is, FERC regulations or NERC compliance standards, but companies use those as a general baseline. And just because you're compliant doesn't mean that you're secure, and that's why a lot of companies choose to go above and beyond what the existing standards are in the name of security. And I think it also manifests itself in a way of thinking about things like cyber insurance. So if you're quantifying cyber risk and you're buying cyber insurance against it from a port operator's perspective, what is it that you can point to demonstrate that you're meeting whatever requirements or mitigation capabilities you can potentially access to secure your systems?
I think if you'll indulge us, I think we've got one last
Sure,
question.
yeah, happy to.
For a nickel.
We're on break now, so you don't miss anything. We are on until 3 o'clock. But gentlemen, if you will indulge us,
we'll stick around.
take one more question.
We're here till 10 o'clock tonight. So.
Thank you.
Sorry, my question is with the foreign ownership piece, trying to avoid the DHS get their hands on it. Is there more of a lean towards using Title 31 to
Yeah, I mean, there's a lot of different potential regulatory hooks that you could leverage. The sort of line that we picked through as we were doing this was, okay, what is the existing regulatory authority around that port security level? And then would they have the ability to extend that to cybersecurity, and could we leverage that somehow? So we were looking at doing this off the top of my head. I think it's the MTSA and SOLAS, as well as the
ISPIS.
Yeah, I think so.
And the MARSEC directives.
Yeah. So seeing that as sort of the most logical and clearly having legal authority, sort of through line to be able to say, okay, they would be able to, with this existing authority, if they wanted to, promulgate regulations saying we are, accepting standards that are established by this independent entity as ones that are going to meet our requirements. It could even do it in the form of the MARSEC directive. That's something that wouldn't necessarily require legislative or executive level engagement to be able to do. And then you could hook in and start supporting it. So there's certainly a lot of legal and regulatory paths you could take. That's just the one we sort of traced through for our paper.
It's not uncommon, too, to see in infrastructure sectors to have a generally accepted standard level that we set that's not formally enforced on any of the entities therein, that it's ultimately adopted by the regulatory authority. So that's certainly happened in the financial industry. That's certainly happened inside the utility or electricity or energy sector, where we establish norms inside of the industry that are ultimately codified and then accepted as regulatory standards at the state or federal level, depending on it. So sometimes there's the chicken or the egg model that goes in reverse, that ultimately you have something that you see is effective and can be implemented by the parties that are involved or the jurisdictional authorities involved, that ultimately is then adopted as a regulatory standard later.
Thank you to all of our speakers. Gentlemen, thank you for questions. Again, we're on networking break now until 3 o'clock, and then the panels and presentations will start up again. So we look forward to seeing you at the rest of the day.